So I would like to tell you, first to thank the organizers for the invitation and for putting together this very nice meeting. I just regret that they put the dinner yesterday, so I could not get drunk, because I was speaking this morning. But there is always tonight. I would like to tell you something about a few recent papers that I did with Sergei Frolov and with Davide Polvara, who is my postdoc, and is really, really excellent, by the way. These couple of papers are about understanding for this mixed flux AdS3 cross S3 strings, the addressing factor and the analytic structure. And there has been also related work by Olaf Olsson-Sachs, Bogdan Stefanski, and collaborators on the same topic, is essentially in between these two papers. And this here with Sergei Frolov is about the matching with the symmetric product orbifold, which you heard about from Matthias Gaberdiel. And these are some results that we developed independently. And we put out the day after their paper with also some comments and corrections regarding what they wrote in their paper. So the mixed flux AdS3 cross S3 cross T4, you might have heard several talks at Integrability in the past several years, but let me just remind you that is a system that depends on two parameters. When you want to study the spectrum, which is what I'm interested, I would even say the planar spectrum. And the two parameters that are important are an integer parameter, which I call k and can be 1, 0, 1, 2, 3, etc. In fact, it could be negative, but it doesn't matter. You can just do a parity and get rid of it. And the continuous parameter, which I call h, and is a continuous positive number. So in the supergravity background, this k is related to the NS-NS flux. And this h is very much like the string coupling, effective coupling of the string that we call G in AdS5 is related to the Ramond-Ramond flux, appropriately rescaled. The tension of the string is a combination of these two. I call it h rather than g like in AdS5 because if you think of knowing some dual CFT, we believe that there should be some interpolating function like h of lambda, a slope function, and you will have to match what this coupling here is with respect to whatever modulus you have in your dual CFT. But this is sort of the idea, the parameter space, and there are some special cases. Yeah, they're all dying, don't want me. Let's see this one. I'm putting them on the side here, but anyway. So special cases. One special case is if this parameter h is equal to 0 and k is whatever else. Can be even a very big number. In that case, the tension is big. And this is a level k Versumino-Witte model, supersymmetric Versumino-Witte model. And you can solve it just by worldsheet CFT. And if you are so inclined, so this was done several years ago, in particular by Maldacena and Doguri, you can also reproduce all this by doing integrability and the ansatz, TBA, the user story, and you can reproduce in this way the known worldsheet CFT approach. Then the opposite case is when k is equal to 0 and h is something greater than 0. And this is the pure Ramond-Ramond case, is related to the D1, D5 system. Comes from the near horizon limit of the D1, D5 system of branes. Is qualitatively similar to AdS5 and can be studied by integrability. And in fact, the S matrix is known, the dressing factors are known, and there are mirror TBA and quantum spectral curve equations for the spectrum of this model. So these were derived relatively recently. Only some particular states have been studied so far. There is more to be understood, but let's say that in principle we believe that we have a good understanding. The general case is the mixed flux. K is not 0, and H is greater than 0. So in this case, our understanding is a little bit more limited, and the reason is that we know that classically this is integrable. This work by Cagnazzo and Zarembo. We can study the symmetries, and we can build the S matrix out of symmetries. In sort of a Bizert way, or maybe Ariotunov-Frollo-Zamaclar way, since we actually start from the sigma model to do this analysis, but up to the dressing factor. And what I want to tell you today, in the bigger part of my talk, is essentially why it is difficult and why we believe that we are making some progress, and we have a proposal for these dressing factors now, which then opens the way to the usual approach of doing the mirror thermodynamic Bethe ansatz or the quantum spectral curve and getting equations for the spectrum. As a remark, the symmetric orbifold is the case with k equal 1 and h much smaller than 1. In fact, what Matthias was telling is essentially can be found by taking this construction that was done in 2014 and taking k equal 1 and expanding everything at first order in H, and then essentially one finds exactly the same symmetry structure and the same S matrix. Another important point is that, I will comment on this if I have time, you reproduce in particular the T4 modes from what you can see directly from the orbifold. So the limit is smooth, even if well, there are some subtleties when you really take H identically equal to 0, and it should be understood why. I will come back to this in a little while, okay? When I will write some more formula. This is what I wanted to say by way of introduction. Are there questions on this while I gear up for what comes next? You can shout them, maybe I will repeat them.
If you have questions on indices.
So, if there are no questions, let me remind you of the well familiar for somebody AdS3 cross S5 story. Let me change board, why not? AdS3 cross S5 strings. So you take these strings, you quantize the model in light cone gauge, you go to the worksheet, and you have a dispersion relation, which looks like this.
Actually, I have a question. So why
Yeah.
insist on H is positive? Because in principle it goes in odd power. So
Well, it's also a choice in principle, but what appears everywhere would be the absolute value. If you do conformal perturbation theory, it's sort of clear that you would get the positive correction. But let me go back to this. So this you know, or some of you know it very well, at least. And I wanted to remind you what's the story there. So what do? One thing that you do is that you say that because of this periodic dispersion, it's not convenient to work in terms of the momentum, but you introduce new variables. And you introduce these Zukowski variables. so that the dispersion relation is a rational expression in terms of the Zukowski variables. They are related to the momentum in some simple way. And they also satisfy a constraint. Of this type. This Q here is a bound state number, so you have a fundamental particle that has Q equal to 1, but then it turns out that you can make bound states with Q equal to 2, 3, and so on and so forth. So this is the structure of your theory, and then your S matrix breaks down into a part. So your S matrix depends on x1 and x2. And there is a part which depends on Q and on x1, x2, which is the dressing factor, and the part which you can determine by symmetry. And the part that you can determine by symmetry is very simple. It's essentially a rational, the entries of this matrix are rational functions in X, whereas this dressing factor is fairly complicated, but we know how to write it, and in fact, let me write the dressing factor, which was found by Beiser-Tate and then Staudacher, in the integral representation, which is due to Dori-Hoffman and Maldacena. I write it because it will also play a role in a little while. So it's a double integral. I'm being a little bit sketchy, like I'm not really writing exactly how the plus minus enter in this thing. Just too much things to put in on the board. And here there is some kernel K. So the best way to write this kernel, and actually the best way to understand this dressing factor, is to introduce a map, a function, or a parametrization U that is related to X simply like this. And in terms of this, then of course you can say that X plus minus are just written as X of U plus minus I Q over G, or something like this. This resolves the fact that these two variables are constrained. And then this K can be written in this way. U of W1, U of W2. So it depends on the difference of these U's. And the form, the explicit form of this kernel, is given in terms of some log gamma functions. Okay, so that's the solution for the case of AdS5, and I would like to maybe stress one point about this fact. Some nice property of this dressing factor that become immediately clear if you think a little bit harder about these x's and these u's. So this u parametrization, or x of u as a branch cut, and you can immediately see essentially that if you compute dx over du, this map here is something like this. So there are singularities whose image are at x equal plus minus 1 in this map. And if you look at the x plane and you look at the u plane, you have that they have branch points on the u plane whose image are somewhere on the x plane. And this branch cut here which I will mark in red. So the two edges of that branch cut, which I marked with these arrows, maybe I could dash one of the edges, are mapped to the circle on the x-plane. And what you say is that for this model, the physical excitation live on this u-plane, which means that they live outside of this circle. And that's why this representation is pretty nice, because it's a contour integral made exactly on these circles. And the way that it is written, you immediately have that there are no funny singularities going on outside of the circle. When you cross the circle, things might get more complicated, and they do, but it's a nice function outside of the circle. Okay, so that's the story for AdS5. Now, how does it change for AdS3? And that's the next order of business. So I will do that in step, and I hope I will have time to get to the end. First, I want to tell you what happens if you do AdS3 just without any NS flux, but just with Ramond-Ramond. So I have now here AdS3 crosses S3 cross T4. So here, this Q you call it M square, and this G you call it H. That's the first difference. Unfortunately, that means that in a bunch of places I have to put H's where there were G's. The other big difference is that now M can be 0. It can be 0 again. It can be plus or minus 1, plus or minus 2, etc., etc. I wrote 0 twice because I'm counting each representation. It is M labels representation. There are 2 with M equals 0. They have to do with the T4 modes. And then there are fundamental excitation with plus and minus 1. And they can make mouse sets. So 2 plus 1 give you a plus 2, plus 3, and so on. 2 minus 1 gives you minus 2, and so on and so forth. But the rest of the story is sort of similar. So here you have to be a little bit careful, because now instead of Q, you want to put the absolute value of M, so that you are sure that this is positive. Otherwise, you mess up your parametrization. But other than this story is very similar, with one important addition, that this phi gets corrected. You get another function here, a function psi that corrects this BAS phase. And this function psi, you just find it. You just find it that it is necessary in order to solve the equation. It will depend on M. And in order to introduce it, you need, or it's intelligent to introduce a nice parametrization, which is something of this form, a gamma, which is related to the x like this. And the reason why this is nice is that then psi is actually psi of gamma of x1 minus psi of gamma of x2. So it's of difference form. And you can write it in terms of, well, psi is a phase, so I suppose I should write the logarithm. It's a product of gamma functions. An infinite product of gamma functions, or if you want, a product of Barnes G functions. So this is what happens for AdS3, S3, T4 when you don't have this K piece of the equation, of the expression. And the new ingredient is essentially this thing, and the feeling that one gets from this phase, and you cannot really be very specific about it, but it's more like a feeling, is that it's related to the new values of M. The fact that now you can also have modes with M equal to 0, and the fact that sometimes you can have M with opposite values necessitates this new piece. So this is where this new physics comes in. Yes? So maybe I'll answer this one later, if that's okay. I'll take these questions later, because I want to get a little bit to the end. So what I wanted to tell you now, which is really the meat of the talk, is when you also turn on this K. So when you have the most general setup possible. And then I also have to remember to address Kostia's question. So, K different from 0, H greater than 0, your dispersion changes even more, becomes even stranger. And this dispersion was originally found by Hoare and Zeitlin and Stepanchuk, I believe. Well, now it's no longer a periodic function. It sort of is periodic if you also change, when you change p by 2 pi, you change m, but otherwise not a periodic function. So you can still try to understand this equation in a similar way. You can still try to say that you introduce x plus and x minus, just like before. Let's see if I can fit it. So you can try to write something like this formula that I had before. But you have to introduce essentially two types of x pluses and x minuses. Let me just write the constraint equation that they satisfy. So this is the same as before. So before here, we had a non-negative number, m. Now, in order to reproduce this equation, we want to put essentially whatever is in this bracket. Okay. So, something like this. The problem is that if I put the absolute value of m, then this formula is good when m is positive, because these two guys have the same sign, but it's not good when m is negative. When m is negative, then I can rewrite this whole expression, because it's a square anyway, as m minus. So I have two choices on my hand. And the choice with the plus, we call it left. And the choice with the minus, we call it right. This is just a sign of the fact that you have broken parity on the worksheet by introducing this K. It's a B field, essentially. That's where it comes from. And then we know that this U-plane is very good for the purpose of understanding this dressing factor. So we want to find what the U-plane is. And again, this, I think, was work of Stepanchuk, who first wrote this relation. But the idea is to now say that x plus 1 over x, well, this is not U, but it is U if you also add k over 2 pi h, that's an h, log x. And this is now U. In fact, this is true for the left x, but you have a different parameterization for the right. where you change the sign. The reason why the log comes in is that it's still true that x plus over x minus is e to the ip. So p is more or less, p half is more or less log x. So that's why you can check that this equation is what you need. And this, on the one hand, is awful, because the logarithm is a horrible function that has a branch cut. On the other hand, is actually sort of nice if you go back and think of this whole story about finding branch cuts. Because you see, here I told you that this map had two singular points here, the images of the singular points here on the x-plane, right? They were plus and minus 1. And if I now repeat the computation, and well, it's possible that I wrote the u over the x instead of the x over the u, but yes. So in this new case, well, I get 1 minus 1 over x squared plus whatever it was, k over 2 pi h 1 over x. So this thing is still something that I can write as x squared over x minus psi plus x minus psi minus. There are still two singular points, and the logarithm is the only guy that would have given me this service, right? So essentially, what happens is that this point here moves somewhere here, and this point here moves somewhere here on the x-plane. So this is sort of nice, and it informs a bit how to write the dressing factor. In fact, now I'm going to make some nice pictures. Remake this picture a little bit nicer. Oh, that's an excellent marker. So for instance, on the u-plane, there is a branch point u plus, which is the image of this x plus. And it's a bit up to me how I decide the branch cuts, but it seems like a nice thing to pick branch cuts that run parallel to the real axis, just like before, only that in this case, this branch cut will go all the way to minus infinity. And then you can ask what is a path that goes just below and then just above. How would it look like? Well, it's something like this. If this is my psi plus, the guy that used to be plus 1 before, it's a path that looks a bit like this. It doesn't quite close. It goes all the way to infinity, parallel to the axis, more or less. But it is more or less what you would like to substitute the unit circle in your story. Notice that in principle, there is another branch point, what I call psi minus, somewhere here. I don't really care because my physical region is outside of this cut. So it's whatever is outside of this curve. So that branch point is hidden so far. But I've been cheating a little bit because remember that this is a plus minus. I have two choices. So this was a good choice that gave me this simple picture. That's the choices, as it turns out, where I have the plus to begin with and the minus here.
So, but the fact you don't see the second branch cut is because you've chosen this branch cut to go to minus infinity.
Yes.
Which
Yes.
Is it justified?
It doesn't really matter because, as I'm going to say, I made this one nice, the other one will be bad. If I made this one bad, the other would have been nice, but conservation of trouble. So, just to address this point, it's a pity that, well, I will keep this formula because I like it. So if I did the other version, so this was left. If I did x right and u right, so here is similar the story. I have a branch cut. The numerical position, the numerical value of this point u of is not u of xi plus, is u of 1 over xi plus, something like this. Doesn't really matter. And the image of this guy, so this guy is here. The image of a contour that goes just above or just below, it looks like this. It doesn't go to infinity, it actually goes to 0. And because of that, you can see this branch point, which was xi minus. And in fact, because this branch point is exactly on the negative real line, and you have a log, the image of this guy is actually 2 branch points. And I take the branch cuts to always to be parallel. And if I now, running out of colors, with my blue pen, I draw a contour like this. This contour is something maybe like this. It runs parallel to the real line. And this other guy would be something like this. So you can define a dressing factor which is given essentially by the BES integrand, but integrated on some judicious choice of all these contours in such a way as that to reproduce crossing and to reproduce the various properties that you want from this model, including unitarity, matching with perturbative computations, and so on and so forth. You do have to modify a little bit this expression, because this expression, you see, it was built in to behave funnily when x is equal to 1 or minus 1, but you can change that, and you can put here xi plus and here xi minus, and then a similar expression for this part of the phase also holds. How much time do I have? Should not have asked me, I should just kept carrying on. Really? Wow. I've been quick. So this you can do, and this is essentially what was written in the paper that we put out in, what, February, March? How to define the phases in terms of essentially these contours and the BES integrand and of these suitably modified difference form dressing factors. One thing that is a little bit maybe unpleasant is that there is this big difference between one type of particle and another type of particle. Of course, parity is broken, so it's not maybe so fundamental, but it occurred to us that maybe it was better to study this problem in the mirror region rather than in the string region. So, of course, the experts all know, but this is the model that we want to study, but then in order to formulate our TBA equations, we need to introduce a mirror model. So what you do then is to introduce this mirror model and to reanalyze these contours. And a dressing factor exists also for the mirror model. That's the case also for AdS5. There is a string dressing factor, there is a mirror dressing factor. They are related in simple ways. But typically in AdS5, one always writes the dressing factor as an integral over the string physical region, over the circle. You could have written it also as an integrand over the boundary of the mirror region. So this is actually quite nice, because the boundary of the mirror region is just a straight line in the x-plane. The mirror region is half of this plane, and because of that, this analysis simplifies and becomes a little bit more symmetric. So let me make a couple of comments before getting there, and I go back to, there was one there. I go back to this expression. To say that mirror is some funny analytic continuation, a double Wick rotation, where you exchange momentum and energy, and you also put an I. And one thing that you find is that the mirror energy, if you just do this transformation here, unfortunately I cannot write the solution H tilde of P tilde in closed form, because I would have to invert some function that I don't know how to invert. But it's not real for real P tilde. That's because in the original model you had broken parity, and in the mirror model you are breaking in some funny way time translation, time invariance, time reversal invariance. Regardless, the energies of the states come in complex conjugate pairs, because essentially the non-reality comes from this term here, but every time you have something with a plus sign, you also have something with a minus sign. So it seems that, as unpleasant as this is, it doesn't have any bad effect on the spectrum. For instance, if you compute Lucier corrections, nothing bad happens. Now, with this caveat, you can go and construct the mirror model for this S matrix. And what you find is that, or what you declare, is that the mirror model should be related to these pictures that I had just by analytic continuation. So this was the string. So the region where the physical excitation of the string live, and the mirror region. So the string region, the good string region, would be this one. It would be this one. The good mirror region is something like this. It's just a half plane for the x left or for the x right. And you have your branch points. One is at this position psi plus, the other is at 1 over psi plus. And then you can look at what the U-plane is. And in the U-plane, the images of this branch point, now you just have two of them, because essentially you are excising half of the plane, so you don't get both of these guys. You take your cuts like this. And one of these contours would look something like this. And the other would look something like this. Just parallel to the axis, and the situation is more nice and symmetric. So this, I think, is a better way, or we think is a better way, more symmetric way to write these phases, and as contour integral over essentially these contours, and to prove various properties. Among the various properties that we want to impose, and with this I will end. So maybe change board once more. Okay. Well, I had suddenly relaxed, but then, okay, let me give you a couple of punchlines and then I wrap it up, okay? So let me rewrite this beautiful formula for the dispersion of the original thing. So the properties that you want from this dressing factor are reality, where it's supposed to be real, unitarity, you also want it to be CP invariant. It's not parity invariant, but it's invariant under parity and sending m to minus m. And then you want to have a nice property where shifting p to p2 plus 2 pi is related or equivalent to shifting m to m plus k. And this is a very interesting property that is not trivial at all. It's very trivial for the representation theory, for the matrix part of this matrix, but it's not trivial for the phases, because you see, shifting p by 2 pi, because p is essentially the log of x, means going through the cut of the log. So it means going through one of these cuts in a certain way. So it means that there are some monodromies that relate these various cuts and that are related to the bound states. Because of this, if this property is true, you need only the first few particles up to k. And in fact, the particle of mass 0 and the particle of mass k are actually related. They are both sort of massless particles. Because the other ones are just obtained by changing the real part of the momentum by 2 pi. This is also related to the fact that, just to go back to the story of the symmetric orbifold, in a symmetric orbifold you basically only see the T4 modes. Because everything else can be obtained from the T4 modes. Well, in the orbifold, in the free theory, it's trivial how you obtain it from the T4 modes. It's just a free theory. But here by some sort of analytic continuation when you deform away from the free point. The last thing that I would like to say is that, to address Kostia's comment, the H20 limit, you can take it and it is fine, but particles start moving at the speed of light. So it's absolutely fine to take this limit when particles move head-on like this, and everything is well defined and you get what you imagine. But when they are collinear, this limit is a bit strange because it gives you some non-perturbative S matrix whose significance is not clear to me. You don't need it to reproduce the Vesumino-Witten spectrum, which you have at h equal to 0. Okay, there were more questions, but I'm running out of time, so I will just answer them during the question time. Thank you.
Okay, let's thank the speaker. So let me first take a question from our online participant with nickname Bogdan.
Okay. Hi.
So momentum has to be real, not from 0 to 2 pi. You excluded minus 2 pi 0 by hand. This is physically inconsistent, just like it would be inconsistent to exclude a part of the real momenta in relativistic theory.
So, well, that doesn't sound like a question. But so
more like a comment, sorry.
One thing that I should say is this. These planes that I described, Bogdan correctly says, essentially, P is log of x, right? X, the argument of x goes from 0 to 2 pi, and essentially this gives you a region of size 2 pi. This plane that I drew. Where is the rest of the real line? Well, you have to go through these cuts, okay? The point is that once you define, if you do it correctly, once you define the dressing factor in the correct way, then you can analytically continue to wherever your hearts want, right? The alternative thing is that you can just, first start from everywhere and construct the phase everywhere else, but it's easier to start from a region if you have a good candidate solution, and then I just extend it. That would be our proposal. I know that Bogdan has a slightly different proposal where he first constructs the whole, or they first construct the whole real line and the neighborhood thereof.
Yeah, hopefully next year we'll have a special event. Put both sides together. So are there any physical participants' questions?
If you shout, I'll repeat.
No, but then people participating online can hear.
I have two questions.
Okay.
First question is, maybe the answer will be short. So usually we know how in AdS3 system to get this dressing factor, just inverting some kernels coming from Q system, Y system, etc., with, of course, injection of some analytic properties. And here, can you do the same, or the Q system was constructed knowing these properties? How is it? What is the state of?
So this is a question that goes to the moderator, but I'll try to answer it. So the Q system was constructed without starting from the TBA and the phase and so on, right? So it was constructed essentially from first principle, Bootstrap principles. Then out of that, one could in principle extract the dressing factor and the various properties. And my understanding, I'm not 100% sure, is that it was checked that the proposal for the dressing factor for the Ramond-Ramond is compatible with the Q system, but I'm not entirely sure whether it has been derived that is really the solution. Whereas for the mixed flux, there is no Q system yet, there is no TBA, there is, I mean, all this should be done essentially.
But well, Q system, system is expected to be the same, but then you also need a notion of shortcut and long cut, and that's a bit funny when all cuts are long.
Yeah.
So
it's not so easy to invert the kernels and get.
Well, I mean, before inverting kernels, one should agree what shortcut means when all cuts go through infinity.
I see. And another question is almost philosophical. I mean, you are in 2 dimensions, so we know that usually we have infinite dimensional algebras like Virasor or Kac-Moody, and there is still no relation between this integrability stuff and those obvious symmetries in 2 dimensions for conformal theory.
So there are some explicit relation between models. So one was the symmetric orbifold at k equal 1. At k equal 0, there is another, we know that the TBA, but we also have a proposal for a model which is some CFT. We know the Lagrangian. This is work by Olaf, Bogdan, and myself in 2014, where we have some candidate model. But the Virasoro part of the story, so the Kac-Moody of the Vedsumino-Witten model, we understand how it fits with the Vedsumino-Witten model. So essentially, the particles of integrability are related to modes of the Kac-Moody algebra. So that's fine. But the Virasoro is a bit trickier because I think that the real Virasoro of the dual CFT, so the Kac-Moody that I'm referring was the Kac-Moody on the worksheet of the Vedsumino-Witten model. But the Virasoro of the dual CFT has more to do with things like multi-particle states than it has to do with what happens in, these are all single particle states, like single trace, single particle in the sense of gravity. So I'm not sure how much of the power of Virasoro you would see in this particular part of the problem.
Okay, thanks.
A quick question. So in pure Ramond-Ramond, the branch cuts you were getting were not quadratic. Is it in U-plane? Is it still true?
Yeah, there are still logarithmic branch cuts here as well. Yeah.
In U-plane?
Yes. Also in the U-plane. The branch point at infinity has a logarithmic monodromy.
Yeah, so just so there are more comments from Bogdan, but I think
Maybe
we should
he can email me.
so there is a list of problems which Bogdan can see, just to add some impartiality, but we'll have to wait to Bogdan, I think, deliver it next year, hopefully, if advisory board will agree with our arrangement.
Maybe for next year we will have fixed the problems.
Let's thank the speaker, and we have a break until later.